ሴሜስተር ወይም አንዳንድ ነገር እንደዚህ ቢሆን የምትሉት ነገር ካለ እድሉን ልስጣችሁና ከዛ ወደ ዛሬው እንትን እንጀምራለን። የሆነ የምንቀይረው ነገር እንደዚህ ከሚሆን እንደዚህ ቢሆን የምትሉት ነገር ካለ አይ ቲንክ ፍሪሊ ማውራት ትችላላችሁ። የሆነ ያልተመቻችሁ ነገር ካለም ማስተካከል ስለምንችል ማለት ነው ከባለፈው ሴሜስተር። ኦኬ ኤልያስ አይ ቲንክ ማውራት ፈልጋል። ኦኬ እሺ
ባለፈው ክላስ ላይ አሁን ማለቴ ፕሮግራሙ ዲዛይን ሲደረግ ፕራክቲካል ላይ ኮንሰርን ያደርጋል። እነሱም እንዳሉን ከማዕድን ሚኒስቴርም ከዩኒቨርሲቲ ጋር አግሪመንት ሲፈጥር አብዛኛው ፕራክቲካል ይሆናል ተብሎ ነው የታሰበው እና አሁን ኮርስ ላይ ኢትዮጵያ ውስጥ ያሉ የፕሮሰሲንግ ካምፓኒዎች ጋር ሄደን ማየት የምንችለው ነገር ካለና ኮርሱ የሚያዘው ነገር ካለ አስቀድማችሁ ነግራችሁን ቢያመቻቹልን። ክረምቱም እየገባ ስለሆነ ሰኔ ከመምጣቱ በፊት ቢያንስ ግንቦት ላይ ምናምን እንድናይ የሚደረግበት ኮንዲሽን ቢኖር ጥሩ ነው። ከነ ዶክተር አቡበከርም ከነ ዶክተር ቡርሃንም ጋር ያለውን ነገር ተወያይተን ማየት ካለብን ይህን ብታው የምትሉትን እንድናይ ቢደረግ ጥሩ ነው ብዬ አስባለሁ።
ኦኬ ከነሱ ጋር ማውራት እንችላለን። አይ ቲንክ ግን ያው እነሱ እዛ ስለሆኑ በተለይ ፊልድ ትሪፕ እንደዚህ ቦታዎችን ሄዶ ማየት ምናምን የሚለው ላይ አይ ቲንክ ሞር ኮንትሮል ያላቸው እነሱ ይመስሉኛል እና አቡበከርና እነሸጋው እነሱን ማናገር ብትችሉ እነሱም ያስተምሯቸዋል ይመስለኛል አንዳንድ ነገሮች ለሁሉም ኮርስ ስለሚጠቅም ማለት ነው። ለዚህም ኮርስ ይጠቅማል ለሌላውም ኮርስ ስለሚጠቅም የሆነ ፊልድ ትሪፕ መውጣቱ አንዳንድ ፕራክቲካል የሆኑ ነገሮችን ማየት የሚለው ኦፍኮርስ እኔም ደግፈዋለሁ ግን ብዙ እንትን የሚኖረኝ አይመስለኝም። ከዚህ ሆኜ ግን ምን ማድረግ እችላለሁ ይሄ ካለ ቢታይ ብዬ ለነሱ ሪኮመንድ ማድረግ እችላለሁ። ከዚህ ሆኜ
ሪኮመንድ ከተደረገ እኛ እነሱን እንጠይቃቸዋለን። ግን ለእነሱም ለእኛም ለዶክተር አቡበከርም ይሄንን ቢያዩ የሚለውን ነግራቸዋቸው ለእኛም ይሄን ብታው የሚለውን እንትላችሁን እኛም እነሱን እንድናይ ኢንፎርስ እናደርጋቸዋለን። ምክንያቱም በጀትም ሲያዝ ብሩም ሲለቀቅ ያንን ታሳቢ ተደርጎ ነው ከማዕድን ሚኒስቴር እንትን የተባለው እና ፊልድ ሄደን ለማየት በጣም ትልቅ በጀት ነው የተያዘው እና እሱ ቢኖር
አይ ጥሩ ነው። እኔም እንደዛ ከሆነ የራሴን ድጋፍ ሰጣለሁ እንደዚህ ቢሆን ብዬ አንዳንድ ሀሳቦች መስጠት እችላለሁ ለነሱ። ስለዚህ ጥሩ ነው። ሌላ አሁን ደግሞ ሳስተምር የሆነ ቶሎ ነው የማወራው ቀስ ብዬ ነው የማወራው ብዙም ስለማላቀው ኢቭን የማወራው ነገር ግልጽ ይሁንላችሁ አይሁንላችሁ በደንብ ስለማላቀው እዚህ ሆኜ አይ እንደዚህ ነገር ነው የሚልም ከዚህ ኮርስ ጋር የተያያዘ ነገርም ብትነግሩኝ ጥሩ ነው። ማለት በሌላ መንገድ ሳይሆን ጀስት እኔ እናንተ ማገዝ ስለምፈልግና ማወራው ነገር ሞር ለእናንተ ሚኒንግፉል እንዲሆን ስለምፈልግ ኦፕን ሆናችሁ የግድ አሁን መሆን የለበትም። ሴሜስተሩን ስንቀጥል ጀስት በወይ ዋትስአፕ ላይ ላኩ ምንድነው ቴሌግራም ላይ ወይ ደግሞ በኢሜል ላኩልኝና እንደዚህ ቢሆን የምትሉት ነገር ካለ እሱን አብረን ማድረግ እንችላለን። ኦኬ ሌላ አስተያየት ያለው ሰው አለ? ኦኬ ፕሮሰስ ሚነራሎጂ ባለፈው ሴሜስተር ወስዳችኋል?
ወስደናል። ባለፈው ሴሜስተር ወስደናል።
ኦኬ ስለዚህ ምንድነው ያሰብኩትኝ ለዚህ ዊክ እና ለሚቀጥለው ዊክ ሞር ከሚነራሎጂ ጋር የተያያዘ ነገር ሜንሽን ማድረግ እፈልጋለሁ። ምክንያቱም ምን ያህል እንደተማራችሁ አላቅም አንደርስታንዲንጋችሁ ምን ያህል እንደሆነ ስለማላቅ ለእኔ ለማስተማርም እንዲቀለኝ ፕሮሰስ ሚነራሎጂ በጣም አስፈላጊ ስለሆነ ዝም ብዬ እንደ ሪቪዥን ነገር ይሆናችኋል። ሜቢ ደግሞ ከተለያየ አስተማሪም ስትሰሙት ሞር እንትንም ሊሆን ስለሚችል እንደ ሪቪዥንም ነገር ቁጠሩት ከፈለጋችሁት። ግን አይ ቲንክ ዚስ ዊክ እና ኔክስት ዊክ ሞር ሚነራሎጂ ላይ ነው የማተኩረው። ምክንያቱም ምንድነው ፕሮሰስ ለማድረግ ወይ ቤኔፊሺዬሽን ለማድረግ ዋናው ነገር ሚነራሎጂ ነው። እሱን ካላወቅን በደፈናው ነው የምንጓዘው ማለት ነው። ፕሮሰስ የምናደርገውን ነገር በትክክል አናውቅም ማለት ነው። ስለዚህ እሱ ላይ ፎከስ አደርጋለሁኝ በዚህ ዊክ እና ኔክስት ዊክ። ኦኬ ኦኬ ሪኮርድ እያደረገ ነው። ሶ should be all good. So and I hope you can see the slides too. Okay. Slide ከታያችሁ I think we can start. So there's not much new here. I'll be teaching you this unit just like last semester, and you can contact me by that email, or if you have any issues with the program as a whole, maybe you can talk to Dr. Shegel, but otherwise we can communicate with the other means as we did last time. And I think the regular scheduled sessions are on Mondays. I think that time works for me as well, so that should be all good. We'll try to have maybe about 3 practicals for this unit as well. And of course, we'll do some problem solving exercises after the lectures as well. So what are we trying to achieve in this course? So I know last semester you went through the first part on mainly comminution and classification, but obviously mineral processing doesn't stop there. We'll do more complicated processing to upgrade the ore, and that is usually using a number of physical separation methods. So we could use gravity methods, we could use even magnetic or static based methods. We use a process called flotation and a number of processes that we can integrate into the flow sheet to upgrade the ore. And therefore, before we do this, we can't just take the material, put it through a mill, and then send it to a leaching tank. We usually have to do some sort of beneficiation, some sort of upgrading the material, so that we deal with only the portion with the highest concentration of the valuable materials in them. And for that, we use a number of methods, and this include either gravity-based or magnetic-based processes as a whole, or for a process like flotation, we use surface-based methods. And hopefully, this is what we're going to be mainly covering in this part. So in terms of what I expect at the end of this is for everyone to have at least a good understanding of the basic concepts in processing minerals. So in this case, it could be processing ores like gold ores, base metal ores, critical element ores, even beneficiation of coal, and so on. So how do we go about processing and upgrade this type of ores? Obviously, depending on what type of ore, we use different processing methods. So we'll try to also understand the different pathways that we use for beneficiating different types of ores or different type of minerals, if you like. Okay, so again, I will expect you guys to have some sort of competency or some level of understanding and working with problem issues related to processing minerals. So if you go to a properly operating plant and you're running the plant, maybe it's working for 2 years, 5 years already, but while we do that, obviously there will be issues during processing. Maybe the grade will drop from time to time, maybe the recovery of the material drops from time to time. So how do we then investigate that, and how do we solve those problems associated with typical processing? Okay, so at least if you have the basic understanding, then you can go about and investigate what issues you might be encountering during a mineral processing operation. And we'll also talk in detail about flotation. That's one of the main methods we use for upgrading ores. And in this case, we talk about the basic principles of flotation. We talk about some machines and equipment we use in flotation and where flotation can be appropriate for which type of ores, for what type of processing. Okay, and the solid liquid part is, or the dewatering part is mainly to do with materials handling. So in this case, most processing plants use a lot of water, and typically water used as a media, and therefore we need to recover the water at the end of the day and be used again and again, or maybe we're just dumping the waste material to tailing dams, but usually we have the opportunity to recover some of the water, and therefore dewatering becomes a little bit more important. So it's not necessarily a beneficiation part. Dewatering is mainly to do with managing the material before it's pumped to the tailing dams, okay, or maybe a way that we use for recovering some of the water to be able to recycle it and reuse it. And as I said, we have a few experiments as well, and hopefully from that, you will do the practical part of the unit from which you collect data and maybe write up a report, which also should help with scientific writing as well. So this is not just this course, but a number of other courses may be used for this purpose as well. And again, we're going to use these textbooks, and these are the ones I recommend, but doesn't necessarily mean you'll find them in your library, but any mineral processing textbook, I think, may be a useful reading, but I think I recommend those ones that I've shown in that slide there. Okay, so I hope the library will offer you some way of accessing those or related textbooks to help you with this unit. Again, I'm going to mainly follow what we did last time in terms of assessments. So 3 practicals, 1 on flotation, 1 on either gravity separation or magnetic separation, and 1 on dewatering. And therefore, from those 3 experiments that we do, you're going to write reports, which are going to be marked out of 30%. You're going to have 1 assignment and also a final exam on the things that are covered in the course as well. And I've also told you what I expect in a report, and that report is going to be a group report. Okay, now Samuel, is someone? Okay, mute ተደርጓል አሁን አይሰማኝም ግን I hope ሁላችሁም ይሰማችኋል. And in that report, I expect you to cover each of these, including introduction, methods, discussion, and conclusion, similar to what you have done in the last semester as well. Okay, so unless anyone has some urgent issues, I will probably just go ahead and introduce the course today and what we're going to be discussing. And as I said, mainly we're going to be focusing on the mineralogy side of things. Okay, so in mineral processing, the whole point of doing it is, we know in a typical ore that you dig from the ground, not everything that you dig from the ground has valuable material in it. So if you say a copper deposit, or when you say a copper ore, what you are actually looking at is a very large bulky material that you dig from the ground. So they're essentially rocks. But of that copper deposit, maybe 5% has valuable material in it. All the rest is considered waste or gunk. So one option you have is to dig everything up, to crush and grind everything up, and then process everything to try to extract the copper. So that's one option. Or the other option you have is apply some sort of upgrading, okay, before you send the material to leaching, for example. So when we say upgrading, as I say, maybe 2% or 5% of the whole ore body is valuable. So with upgrading, all we're trying to do is separate out that 2% or 5% first. Okay, so then the 95% will be a waste. I don't need to put that through a leaching tank and dissolve it in acid and so on, because there is no value in it. And if I do that, I'm going to waste my chemicals. So I'm going to waste money doing that. And therefore, there's no point to do processing of the whole material. So with upgrading, what we do, or with beneficiation, what we do is separate that 2 to 5% valuable, separated from the waste, and then you can take that valuable and put it through a more complicated processing. So this involves maybe further grinding. So then further grinding can be followed by leaching or pyrometallurgy if you're using a pyrometallurgical method. So in this case, either I can put it through a leaching tank or I can put it through a smelting operation. And both of them can be handled, because instead of putting the whole material through a leach tank or the whole material through a smelting, I will just do only 5% of it. And therefore it's a lot more cost economic and it saves you a lot of money doing that. And therefore the whole point of mineral processing is just separating that valuable material. So in the previous semester, what you were doing was do the first two parts. Those are the comminution, which is mainly reducing the size, and also doing size management, where we can classify material into coarse and fine. So in a way, we were preparing it for further processing. So last semester was all about size management and comminution. Now, once you have done that, naturally, you have to go up with the next step, which is the beneficiation or the concentration. And that's what we're going to be covering in this course this semester. Okay, so this semester will be more about concentration, which can be using physical or chemical properties of the minerals. And we'll talk about all the different type of concentration methods, and we'll talk about dewatering or solid liquid separation as well. Okay, so it just follows up from here. And obviously, once we produce a concentrate, then I'm thinking you are also taking another unit on hydrometallurgy, so you can follow up with a process involving either leaching or smelting as required. So when you look at a typical ore, I don't know if you see my arrow there, but so I just picked a gold processing plant here, but it could be an iron ore or it could be base metal ore, whatever it is that you're dealing with. Usually looks, at least it will involve certain stages of crushing and grinding. Okay, so in this case, for example, for this particular gold processing plant, we have unmined ore coming in trucks, and you put it through a gyratory crusher and a SAG mill. And we have a screen next to a SAG mill, which can recycle oversized material or send to a ball mill and a classifier. So that was all about what we covered last semester. But then you can take this one and now put it through a concentrator or put it through a beneficiation plant. So in this case, once the material passes through a SAG mill and ball mill, we can, for example, do concentration using a Nelson concentrator. If it's a gold ore, typically we use, for example, a Nelson concentrator, which is a gravity separator. Okay, so we did not cover this part last semester, but now once we do crushing and grinding and sizing, the next step will be either to use a Nelson concentrator or a gravity concentrator. So in this case, you could use other things. You could use tabling, you could use, as in this case, Nelson concentrator or jigs or whatever the case may be, okay? Another way of doing it could be, for example, you take the ground material and put it through a flotation tank. So obviously, whether you use a gravity method for separation or a flotation method will depend on the nature of the ore you are processing, okay? So in this case, this plant, for example, because they have different type of ores, maybe for 2 weeks, they will run the gravity separator. Maybe this is for high grade free milling gold. and then they will turn that off, and then the next time for another 2 weeks or 3 weeks, they will run the flotation plant and separate more complicated, fine material using flotation. So you can, for example, run the plant on campaign based. Okay, so maybe a couple of weeks on one separator for a different type of ore body, couple of weeks on another concentrator using, or because you're processing a different type of ore. So that can be a possibility. Okay, or sometimes you could take only the coarse portion to go to the gravity concentrator, even for one ore body, and then the fine portion can go into, for example, in this case, a flotation cell. Okay, so depending on the nature of the ore, you can work with different separation methods, concentration methods, and obviously at the end of the day, you want to maximize the recovery of gold if it's a gold plant by using a combination of different separation methods. So why don't we stick to one of the concentration methods? In this case, for example, why these guys are not using just the Knelson concentrator every time? Because they know the ore body is variable. At some point, it becomes more complicated, more fine. So the gravity separator may not be able to handle that properly, and there will be some losses. So depending on mineralogy, you have to adjust for which processing method you're going to use. Okay, so that's very critical. And how do we know which to use? We have to first have a very good understanding of mineralogy of the ore body. Because for some ores, even if it's a gold ore, maybe gravity separation doesn't give you much benefit, so you may not be able to use it. Okay, for some ore, you may not use flotation, especially if it's an easy to process ore. We call it a free milling gold ore, for example. If we just use gravity concentrator followed by leaching, maybe that's enough. Okay, you don't have to use flotation. But more commonly, because our ore body is variable, some point it is easier to process, some point it's more complex to process. You have to adapt for that variability in ore body, and therefore you have to try different processing methods to maximize recovery. So that's why people who run plants for many years, they will make sure they have a very good understanding of the mineralogy of the ore body, how it is varying over time, and when they, for example, take the ore from underground mine versus from an open cut mine, okay, they know the mineralogy varies, and therefore they have to account for that variability. And one of the methods of doing that is by simply changing the processing flow sheet depending on what's coming into the plant. Okay. So obviously, once we concentrate, either using a gravity method or a flotation method, then this can now be sent for further extraction. Typically, we do leaching. So the leaching can be done. For example, if it's gold ore, we can do leaching with cyanide and so on. I think this is what you should be learning in hydrometallurgy. So that's what follows a typical concentration methods. Okay. Or you can follow it straight with smelting. So it depends on, for example, if it's a nickel or copper ore, once you concentrate, you can send it directly to a smelter. Okay, so you don't have to do leaching. So again, it depends on what you're dealing with as well. So again, I think I've showed you something like this in the past as well. So obviously, when we discover ore bodies, we are typically interested in those with higher concentration of the valuable commodities, so of copper, of gold, or lead, or whatever the case may be. And that's due to the fact that some ore bodies have an abundance of certain minerals. So we know already if we want cobalt, we know what type of minerals we're looking for. If we're interested in copper, we know what kind of minerals we're interested in, and so on. So again, before you design your flow sheet for processing, understanding mineralogy becomes very important. Because as we said last time, we know mineralogy controls what kind of equipment you buy. So this can be, for example, the crusher or the grinding mills you buy in that plant is dictated by how hard or how soft the ore is. So mineralogical assessment tells you how hard or how soft the ore body is. And mineralogical assessment tells you whether coarse grinding is enough or whether you need to do very complicated fine grinding. So in this case, from assessment, we want to know association of minerals with one another. If it's the copper ore, is it just chalcopyrite, or do you have chalcopyrite, chalcocite, and a number of other minerals together? Because that will make a difference in processing. Or is it just a sulfide copper or an oxide copper? Again, that dictates what we're going to do for processing. Obviously, composition, and we talked about grain sizes, distribution, and so on as well. So all of these will help us understand what we're going to do next for concentration, whether we're going to choose gravity separation or flotation is going to be dictated by the nature or the mineralogy of the ore that we're processing. And for mineralogical studies, we can use a number of methods, okay? Typically microscopy, we can use methods for quantitative analysis. You can use something like an AS or an ICP, for example. Or for further mineralogical studies, we can use electron microscopy and so on. So probably what I thought for today was maybe go through some of these methods and let you know what information we find from using these methods, okay? So that we have the bigger picture. If I just go straight into mineral processing and talk about gravity separation or flotation, I thought it may not necessarily make much sense. But if we have an idea of how we can work out proper mineralogy first, then you will understand why I will need to do flotation based on that particular mineralogy. Okay. Or I may say, oh, flotation is not going to work because this mineralogy tells me this and this and this. So there's no need to apply flotation method because you're not going to gain anything from that particular operation. So already having that good understanding of mineralogy is going to dictate what kind of pathway I'm going to use. And that's why I thought it's very important to talk about it, okay, beforehand. Okay, so before I continue, does anyone have a question? No question? Okay, so again, when I talk about these methods, I'm not necessarily talking about some generic thing. I will just tell you, because one is not the purpose of this course. What I'm trying to do here is just try to focus your understanding to how we use these methods for mineralogy only, okay? So yes, you can use these methods for a number of other things, for biology, for geology, for other things, but that's not what I'm going to focus on. I think my discussion here is only restricted to how we can apply these methods to understand mineralogy, and that understanding of mineralogy is going to help us with mineral processing later on. Okay, that's just how I'm going to discuss it. So it's going to be just a brief discussion of each of those methods, okay? So now you go out there, you are maybe you doing your geological exploration, maybe all your methods imply that there's a significant deposit somewhere. Okay, so maybe you're interested in investigating that further. And probably what people tend to do is once maybe you have a drill core that you're working on, or whatever it is. So initially people have a quick observation of what it is, but then they want to know the potential of that deposit, whether you can actually get any value out of that deposit. And following your geological studies, you typically follow up with some kind of metallurgical understanding of that ore body. So obviously, if you have an idea already, maybe you have worked out that it is a base metal deposit or maybe a copper or zinc deposit. Okay, let's just take a simple case scenario there. So you have two options there. So you can maybe send this to the lab and quantify exactly how much copper or zinc is coming back from that sample. Okay, so it could be, a reading could be 2% copper Okay, maybe you have taken 100 different sites and you have 100 different samples, and all those 100 samples most likely will give you different results. Maybe the average of the 100 sample comes at 2% copper. So obviously there is a potential there, okay, for going after it and try to maybe recover some of the copper, or this is a potentially good deposit to go after. So this assay simply tells you there is 2% copper. It doesn't tell you much after that. So if then you take that and ask a metallurgist or someone who is designing your flow sheet, now I have 2% copper and it's a very large ore body, I want to, go and process this material, they're not going to get much information from just knowing it is a copper deposit and it has 2% copper. They want more information. Can you guys see my slides? Did someone share a different thing? Can you see it now? I think something happened and my slides were stopping sharing, but hopefully you can see it now. Okay, so if now we say 2% copper in the deposit, and I give this one to someone who is developing my processing flow sheet, they're not going to get much information from that. So they will tell you, give me more sample. I want to find out what is in it and how the copper is being hosted in that material. So 2% could be 2% copper in oxide form, or it could be 2% copper in sulfide form, or it could be maybe half-half. Maybe some of it is as an oxide copper, some of it is an sulfide copper. Why do we care about whether it's copper sulfide or copper oxide? Because unless we know it is a copper sulfide or a copper oxide, we can't process it blindly. Because if you tell me it's a sulfide copper, I know I'm going to process it differently. If you tell me it's a copper oxide, I know I'm going to process it differently. Okay, so I want to know, just knowing 2% copper doesn't give me much. I want to know how is this copper present? What is the mineralogy of that copper in the ore body? So one of the things you can do is maybe run an XRD. Okay, XRD tells you actually what phases do you have in that sample. So in this case, you could say, okay, I have 50% oxide copper and 50% sulfide copper after doing XRD. Not only oxide and sulfide, you actually know exactly what sulfide of copper you have and exactly what oxide of copper you have. Okay, so when I say oxide of copper, okay, could be malachite, could be azurite, could be some carbonate of copper in the ore body, which is common when you look at the ore body zonation. Usually the oxide zone is dominated by this species. If you go deeper, if the sample was from a bit deeper in the ground, you are more likely to find the primary sulfide zone where you have the sulfide-based copper. So in this case, maybe you might be likely to find a chalcopyrite, which is another copper sulfide form. So for someone designing the plant, this is actually very important because, as I told you, I have to know whether this is a copper sulfide or copper oxide to be able to tell you how to process it. So today I'm not going to tell you processing methods. I'm going to tell you first, have a very good understanding of the mineralogy. So run it through XRD, comes back with the result. Maybe from that, 70% or 75% is chalcopyrite, if you're lucky, from that deposit, especially when you're only looking at the material containing the copper. And the remaining could be associated with something else, okay, maybe an oxide or a carbonate or something like that. But XRD doesn't necessarily tell you what you have in copper or the copper form, but it also tells you what gangue materials you have as well. So I run XRD, I say, From the XRD, I know I have the sulfide forms of copper in these minerals. I have these minerals that are the gangue minerals typically I find in the ore body. Then now I have a good picture of what to do. One, I can design a flow sheet to target the minerals containing the copper, but I also target my flow sheet so that I can reject the gangue as well, because I know what to do to reject the gangue in the design of the plant. I know what to do to recover the copper containing ones. Okay, so my flow sheet or my processing design is not blind, it's actually because of the mineralogy of the ore body. So I'm designing it based on my understanding of that. But for those who are not familiar with how XRD works, if you pick a rock sample, as I said, maybe, I don't know if you remember, but I said minerals are crystalline materials. They're made from ordered arrangement of atoms. So in this case, when I say chalcopyrite, we know it's copper, iron, and sulfur making up the chalcopyrite. And the way the crystals of chalcopyrite are made is based on how the various atoms within the chalcopyrite are linked with one another. So copper is linked to the sulfur and the iron in a way, in a specific way, to give rise to a chalcopyrite crystal. So when you look at a chalcopyrite crystal, you have actually a lot of crystal planes. Okay, so that picture there at the bottom is simply showing you what we mean by planes in a crystal or in a mineral. Okay, so if you follow a certain line, so you can actually see that ordered arrangement of atoms in a crystal will give you different planes. And now a copper sulfide, for example, a chalcopyrite mineral will have a unique crystal plane. So what do we do in X-ray diffraction? We subject the sample to X-rays. Okay, so there's an X-ray source that you subject the sample to, and you can either rotate the sample holder in the XRD machine, okay, or you can just rotate the particles in the sample holder. You can actually do it in different ways. But in any case, X-rays hit the sample, and from that sample, you have X-ray reflections coming back. So X-rays hit the sample at a specific angle theta, and the sample reflects X-rays at that specific angle theta. And those X-ray reflections from the sample actually come from the planes in that crystal. So each of those planes will reflect the X-rays at some unique angle. Okay, so now I have a powder sample which I've ground. Okay, so it's a milled sample, it's a rock sampled, put it through an X-ray machine, subjected to an X-ray, and based on the angles of reflections I have from that sample, so I collect the angle of reflections, and then I say, okay, there are this angle of reflections coming from the sample, okay, at these angles, and we know the angle of reflections come from specific crystal planes. And we know also minerals have, so for example, if it's a chalcopyrite has a unique set of planes. If you look at sphalerite, it has a unique set of planes. If you look at monazite, it has a unique set of planes. So the reflections, the X-ray reflections coming from the sample are very specific to the minerals that you are observing. Okay, so what all we have to do is record the reflections of X-rays from the sample, okay, and those will be recorded in the detector, and you would have an X-ray spectra, which looks something like this. So in this case, if I had sphalerite, I know sphalerite is made from ordered arrangement of zinc and sulfur atoms, and there are a number of planes within sphalerite crystal. From those planes, I will get different X-ray reflections. And those X-ray reflections can be recorded and can be presented as a spectra, which is what you see here. And as you see here, for example, there will be a characteristic spectra of sphalerite at 28.572 theta, for example. And you look at another one, there's one at 33, there's one at 47.5, there's one at 56 and 69. So as I said, these reflections come from specific planes in sphalerite. So in other words, there are no other minerals that have exact same reflections of X-rays as sphalerite. So no other mineral will give you this exact set of reflections at these exact angles other than sphalerite. Okay, so that's why it is very specific. So whatever spectra you see for a given mineral is very specific to that particular mineral. And we actually know, we can calculate out where those reflections are coming from, and the planes can be calculated as well. Okay, I'm not going to go into those details, but at least all you have to know here is I put a sample through an XRD machine, I record the X-ray reflections coming back at those specific angles, and then I try to match those spectra to what's known already. And if it matches that of sphalerite, then it must be because it's sphalerite. If my spectra match chalcopyrite, then it must be I have a chalcopyrite in the sample, and so on. Okay. So these are how we run X-rays, and therefore at the end of the day, you should be able to find the phases, or if you like, the minerals that you have in your sample based on the X-ray spectra that you collect. Okay. And you can do that for a pure sample, like the one I showed you for sphalerite here. Okay, so this is just showing only spectra of sphalerite. But obviously, when you dig something from the ground, you mill it, most likely you have maybe 10 different minerals in it. Okay, because it's a rock, and a rock is not going to be pure sphalerite, or it's not going to be pure chalcopyrite. It's going to be a mixture of sulfides, oxide, maybe some silicates as well. And in fact, the majority could be silicate. So it's a mixture of minerals that you dig from the ground. So when you put through an XRD, it could also be a mixture of minerals that you're looking at. But as I said, each of those minerals in the sample will have specific spectrum. So galena here, for example, has specific spectrum. Sphalerite has a specific spectrum. Pyrite has specific spectrum. So my sample gives me lots of spectra at lots of angles, but I'm going to then allocate each of those peaks to a specific mineral or a specific phase, because I know different minerals will have reflections at those different angles. So at the end of the day, I can actually match. If I have a mixture of minerals, for example, I can match each spectra or each peak to what it is in the sample. And this is what this figure here shows. Okay, so lots of spectra, but when you look at the main peaks here, you can actually find what they belong to. Okay, so in this case, they have been identified, and this spectra here is telling us that in the sample, you actually have lots of minerals, so about 6 of them are shown there. You may have also smaller, minor amounts of other minerals, but the XRD may not pick everything. But at least it will give you the majority of the sample that you're looking at and what is in there. Okay, some minor phases may not be picked up in an XRD. Okay, so obviously for someone who has used XRD before, they know what I'm talking about. So once you run the material or you sample through an XRD, you get a spectra, then you match it with what is out there. So we have a database of pretty much all the minerals that we have found so far. And that database is basically used as a reference, and we try to match our spectrum to the one that's available in the database and match it with the one that's close to what we have in our sample. Okay, so that's how they work. And usually, if you have an XRD machine, you should have a software that helps you match your spectrum with that of the database that you can find, and then you'll be able to tell what's what. Okay, so why am I talking about all this? Because this is pretty much the first part you have to do before you do mineral processing. You have to know what you have in the sample or in the ore body. So in this case, for example, we run the sample and we have galena, sphalerite, chalcopyrite, energite as the main phases coming up. So maybe initially you were just discovering this for copper. Okay, maybe as I said, maybe this material has 2% copper, as I said earlier. If you did assays for other things, maybe now you have some galena there, so you have some lead in the ore, you have some zinc in the ore. And these are also potential products. But when I know I have 3 different sulfides there with 3 different products, I'm going to have a specific processing plant for this. If I have just copper in the plant, then my processing is going to be a lot more straightforward compared to when I have 3 commodities that I'm interested in. So unless you understand what you have in the sample, what you have in the ore, you're not going to go and just rush into processing it, because there could be some potential products that you can collect along the way as well. The other thing is, from this, I know now I have chalcopyrite and energite for copper, which are both sulfides. Then I know what kind of processing flow sheet I'm going to design, because my sulfide is mainly, my copper is mainly in sulfides. Okay, so if I did the same thing and I came up with copper carbonates, then my processing is going to look completely different. Because what we do for copper-based, oxide-based copper is different in terms of processing compared to sulfide-based copper. Okay, so phase identification is one of the things that are very critical before we do mineral processing. Okay, so I will talk about the next method we use, but is there any question on X-ray diffraction so far? Or maybe is it matching what you understand before, or is something confusing? You want more information about it? Just let me know. All good? Okay. Now you have run XRD, you know you have, say, chalcopyrite and energite, but you don't know much about the particle size. So if I gave you now, initially I say I have 2% copper, and now I add a bit more information to it, and I say actually the copper is in the form of chalcopyrite and energite. Then I tell you, okay, how do I go about and process this material? Maybe I ask you, how fine do you think I need to grind this? Okay, to liberate the particles. Because if you remember, last time we said liberation is very important. So do you crush and grind it to about 150 micron? Do you grind it to 100 micron? Do you grind it to 500 micron before you process it? We don't know, because all we know is we have sulfides there. We don't know anything else. So we need to do some other method to observe particle size, because particle size will be determined by liberation. So as I said last time, the whole point of doing grinding is liberation. So when you say I'm going to grind it to 100 micron, it is because I'm going to liberate the majority of the particles at 100 micron. And that's based on mineralogical study, okay? And if you go to a plant and they say the grind size is 150 micron, because they know at 150 micron, they can liberate most of the particles. but XRD is not going to tell me that. Okay, or just looking at the material physically, I can't tell. So you need to do something else to get an understanding of particle size, grain size, liberation, and so on. Okay, so that's why we need another information, and that information is usually done using electron microscopy. Yes, you can use scanning electron microscopy for a number of other things, especially in biology and so on. But it is also very important in mineralogical studies. So I'm also going to tell you, maybe you know how it works and all that, but I'm going to tell you how we use it in mineralogical studies so that you have an understanding of what information we get from scanning electron microscopy. So obviously, as the name implies, we use electron beam. So the sample is basically subjected to electron beam, and that electron beam is scanned over the sample. So in XY motion, we get, now we're subjecting the material or the sample to electron beam, and then you get, the emission you get from it is also an electron. When you hit a material with electrons, you could get either secondary electrons bouncing back from the surface, or some electrons may penetrate a little bit deeper into the sample and they're going to be scattered back again. And that is called backscattered electrons. So you can then take these two secondary electrons and backscattered electrons coming from the sample, put it through a detector, and get an image of the sample you're looking at. Obviously, because you're using electron beam, which is very tiny in dimension, you actually get a very high magnification of the sample. So we're looking at maybe 1 micron, 2 micron, 5 micron size. So it's a very detailed image you get. If you use a simple reflected light microscope or say an optical microscope, the resolution is not going to be that high. But with electron microscope, we can actually look at small grains very close to few microns and observe those grains in detail. Okay. So in this case, what happens when you subject a sample to a beam of electrons? You could have secondary electrons coming back, backscatters coming back, even characteristic X-rays coming back. And basically we take that and the detector will use that information to give you an image that looks like this. Okay, so maybe this is for a polished section, okay, which maybe is a powder sample, you make a polished section out of it. Or if it's a block sample, you can also make a block sample, which is also polished to very fine finish. But regardless, an SEM or electron microscope can give you something like you see in that image there. So some spots appear dark, some appear a bit lighter, some are very bright. So this is dependent on the signal coming back from the sample, in this case, a backscattered electron signal. And from this, you can see different grains in the sample. Okay, some grains are elongated, some are large, some are very tiny. But obviously, I can work out that I'm looking at different phases in there. For example, the dark ones tend to be either oxides or silicates. The bright ones are usually heavy elements. So if you have lead or gold or something like that in the sample, they appear to be very bright because they're very reflective. Okay. If you have sulfides there, they tend to be intermediate, not very bright, not very dark, somewhere in between. So this is what a typical backscattered electron image looks like. So an experienced person can maybe roughly work out what's going on, but it's not going to tell you whether you have this mineral or that mineral. It only tells you that you're looking at the, if you like, the texture of the sample. Okay. If I'm interested, if I already know, if I've run this, say, 100 times, and I already know what these are, then I can easily tell what they are because I've done this many times. I have characterized it. I have a good understanding of what I'm looking at. But usually, if you're looking at it for the first time, you can only guess what they are. So I can already say, okay, looks like maybe there might be some gold there because some spots appear very bright. And you could say some spots are dark and that looks like a silicate material. So maybe the gold is hosted in a silicate material and so on. So I'm going to be very, I don't know, rough or not so detailed in my conclusion if you're looking at for the first time. But regardless, this is a starting point to work out what information we might get from a sample, but I want more information. So I say, okay, I'm actually want to focus on the one that says sulfide here, and I want to know what sulfide it is. Okay, is it chalcopyrite? Is it pyrite? Is it sphalerite? Whatever sulfide it is, I want to know that. Okay, how do we do that? We take this and couple it with what we call energy dispersive spectroscopy, or EDS. So for each of those grains, I focus on one of these grain, okay, whether the bright one or the dark one or the gray one. And I can take EDS readings from each of those grains and I can exactly work out what they're made of. Okay, so that's why we usually couple an SEM image with some sort of analysis to help us identify what each of those grains are. And one of the things we do is to use EDS, or energy specific spectroscopy, where in this case the SEM is coupled with an EDS, where in this case I subject those small grains on my sample to X-rays and I record the excited X-rays from those grains. Okay, usually those X-rays are emitted at very specific energy. So if I have copper there, I will have a very specific emission for copper at specific energy. If I have zinc there, I will have a specific X-ray emission for zinc at specific angle, and so on. So if I have any element in that sample, I will have a specific X-ray emission for that element. So already by doing EDS, I know what element I have in those little grains. So I go back here and I say, this says sulfide, but what comes from my X-ray reading is mainly copper. If it's, for example, let's continue with chalcopyrite. If it's chalcopyrite, you should have X-ray readings as copper. You should have some iron. You should have some sulfur. Okay. Now, if you have those and at the correct ratios, then maybe you can work out that it is chalcopyrite. If your ADS is saying you have zinc and sulfur, mainly coming back, then it's most likely going to be sphalerite or something similar. So by looking at the elemental information coming from each of those grains, I will be able to work out what mineral it might be that I'm dealing with. If it's gold, then I will have X-ray emissions for gold. Okay, so that becomes now a little bit more specific. Now, yes, the energies will tell me what element I have, but the peak height will tell me the abundance of it as well, how much. Okay, so then I can couple that and I can get quantitative information as well. And therefore, usually when we do SEM for mineralogical studies, we usually need an information about elements as well on the sample. When we combine the SEM image with elemental analysis, we get a more complete picture of what's going on. Okay, so again, to work out issues to do with, for example, mineral association with one another, okay, or if I wanted to work out what each of the various grains I'm seeing in an SEM image and so on, I take the SEM image and the EDS image together to work out what am I looking at, okay? So now that I have coupled those information, and in this case, for example, the EDS tells me that I have copper, I have iron, I have sulfur, and with these peak ratios, typically if you have a chalcopyrite, the X-ray spectrum of chalcopyrite looks like this one, because we know chalcopyrite is made from copper, iron, and sulfur. I can go into detail and talk about what K alpha for copper is and K beta for copper is and so on. I don't know if you learned this one, but it's all to do with the transitions happening. So when an X-ray hits copper, obviously the copper is made from K shell, L shell, M shell, and so on. And usually in this case, if you say copper K alpha, it means the X-ray is emitting or ejecting an electron from the K shell. Okay, so once that electron is ejected from the K shell and it comes back, and you have, once, for example, you emit something from the K shell, there has to be an electron coming from the next shell to fill that K shell, because the K shell is the lower energy state. And if it comes from the next shell, which is the L shell, you have K alpha emission. If it comes to the next level, then you have K beta emission, and so on. I think probably that's more technical. I can talk about that for a day, but that's not important. But the point here is, for my sample, I can take EDS readings, which gives me an X-ray spectrum, which tells me what mineral I have in my sample. Okay, so any grain that I see on an SEM, I can take it individually and analyze it and tell what it is, basically, what mineral it is that is made of. And we can do quantitative analysis as well for EDS and determine how much elemental proportions that we have in a given sample. Okay, so again, so this is maybe an SEM image that you're looking at. And as you can see here, the SEM shows you a very unique grain there. And maybe you want to know what it is. All you have to do is take a spot analysis and determine what elemental proportions are coming here from this particular grain. And when we do that here, for example, it comes as iron and sulfur, and they have worked out that this is a pyrite grain. I can do the same for any grain that I see on my sample. Okay, so that's what we call a spot analysis, to work out the particular type of mineral that I'm looking in the sample. So how do we work out liberation? How do we work out mineral association? All those information that are really useful during processing. To do that, you need image analysis. So what do you do with image analysis? Now you took an image, you have run EDS on it. Then basically you're trying to work out what each of those grains are on a given sample that you are looking at. So maybe this is not that important, but let's come here. So as I say, this is a typical backscattered electron image from SEM. When you look at that, yes, you see some grains there are a bit darker, some are a bit grayish, but it's very difficult to tell what they might be. Okay, so a backscattered image is very good for biological samples. Maybe it tells you morphology of the specimen you're looking at, but it may not be very useful for mineralogical work. It is only an initial work. We need to do more to get complete information about the sample for mineralogy. So what we do here is we take each of these grains that look different color or different grayness, and we just work out what they might be. Okay. So in this case, you need to do what we call image processing. As you can see here, from there, I have now come up to something that's very colorful here. Okay, which tells me at least I have different things here. So the orange stands for one particular mineral. So if you look at this big one here, or these ones at the bottom here, they're made from one phase. So they have one mineral, if you like. The other colors that are shown here belong to other minerals. But how do we allocate this color? Because what we have here doesn't tell us a lot of difference in the specific grains that we're looking at. But here, it looks a lot more nicer, it's a lot more distinct. So I can pick a particular grain here, for example, this one here, and say it is actually made from a lot of phases, which means a lot of minerals together. And it's not actually a liberated grain. But likely all the other ones don't look like it. So most of them are actually liberated sufficiently. But what you need to know then is how we allocate these colors to be able to work out the mineralogy of the sample in a more detail. To do that, we need to take backscattered images and, as I said earlier, secondary ion, backscattered images and X-ray readings. So the grayness of the atoms or the grayness of the image that you saw there is dependent on what we call mean atomic numbers. I'm not going to go into details about this one. You guys can read it if you want and how we can calculate grayness. But typically, silicates have a low mean grain or a low mean atomic number. That's why they appear very dark in secondary ion image or backscattered image. Materials that are heavy or minerals that have a large mean atomic number, such as, for example, tetrahedrite or arsenopyrite or gold, they have large mean atomic number and they appear very bright in secondary ion image. So when you look at that, we can only comment on that. We can look at that and say the very dark ones are most likely silicate. The very bright ones are maybe heavy element dominated minerals. Maybe it's galena, maybe it's gold, something like that. The intermediate ones could be more oxides. So you're not going to say by looking at that, this is exactly this, because you don't know, but you can only make rough comments based on the grayness or the brightness of the material. And that's, as I said, related to the mean atomic number of what is making up those grains. So from something like this, I need more information, more quantitative information telling me this grain is made from copper, this grain is made from zinc and sulfur, whatever. So I need that specific information. And that's why we need to do an X-ray based method. Again, if you want, read through this one. But basically what we do is we take this grain, for example, the blue one here, subject it to X-ray readings or EDS, and work out what element is made from. And I take another grain, do spot analysis on it, and work out what elements are making that particular grain. And then I know what mineral it is. So basically for all the colors you see here, we apply the same techniques to individually characterize each of those grains. So we say, if this is, so again, these are image analysis methods are software-based methods. So you say, if the element comes as copper and sulfur with this proportion, you can allocate that to chalcopyrite. If the reading from X-ray comes as iron and sulfur in this proportion, then you can allocate that to pyrite and so on. So this is already done automatically in the software. And from a sample, maybe you might need to do 2,000 readings or 2,000 individual grain analysis to have a more complete picture, okay? But maybe you can do this over a couple of hours. Nowadays, the image analysis softwares can do a lot of work. Back in the days, people used to do this manually, take a grain and try to work out what it might be and so on. But these days, we can automate this and we can work out exactly what they are. So I say, take a grain and analyze. Or another method is what we call the PXMAP. And in this case, you take the particular grain that you are interested in and you get a lot of X-ray readings from it. Okay, so maybe you can go grid by grid. So those dots that are shown there are actually readings of X-rays from those points. So you could do, say, on one grain, you could do hundreds of X-ray readings. And as you see here, so maybe this one here is done for a number of readings. And based on the readings that come back, we say, okay, we can now allocate different minerals to that grain. So the greenish one is pyrite because it's mainly iron and sulfur. Then you have orange, that's chalcopyrite. You have reddish one, that's galena. That is based on, by taking one grain take hundreds of X-ray readings from it and map that onto the grain and work out what you have there. Okay, so this is a lot more accurate, tells you almost conclusively what minerals and what grains you have in a particle, and therefore can be very informative in terms of working out mineral association. For example, when you look at this, you can see the orange, the red, and the green are very intimately intertwined with one another. It's a complex association. And that's one of the information we get from mineralogical work. So before I, for example, decide my grinding mill, I already know here that, okay, grinding is going to be a lot more complex because the particles I'm looking at here is telling me the grains for chalcopyrite, pyrite, and galena are very fine. Okay, so if I did grinding to 500 micron, it's not going to help because all these minerals will be still together at 500 micron. Maybe if I do at 50 or 25, I may have some luck in separating them out or breaking them apart from each other. I liberate them. So then I can think about what is the grinding mill I'm going to buy to be able to do this. Okay, so am I going to do ultra fine grinding, or am I going to do a regular ball milling, or am I going to get away with a SAG mill? All those will come into effect just based on the grain size that we're looking at here. So that will be one input into our combination circuit design, as we said earlier. And also say, for example, in this case, most of them are sulfides. Looks like flotation is a good way to approach this problem. So again, with image analysis, what does the software does for you? It will take the original image and you can then do what we call background subtraction, because now you have a powdered or a milled sample, which is dispersed in epoxy, and therefore the epoxy will be picked up in the image. So that dark area there is basically the background. So the very dark one is the background. So you can do background subtraction. Now you have the particles without the background. And once you have the particles, some of them are attached to one another. Maybe you can deagglomerate them as well. And now you have all these particles that you can individually analyze and allocate different phases to each of these grains. And you can do it using the software. So basically you say, I'm interested in this one here. What does this grain look like? You take a grain, for example, here. And as you can see here, looks like there are two colors there. At least one looks a bit darker gray. The other one is a bit lighter gray. So surely there are at least two phases there. But maybe you want to know on the edge here, there's something there. Is it the same as this one? I don't know. So there's a small dark dot there. Is it the same as the big dark dot? I don't know. So you can actually take different readings from each of those spots and see what they are. And that's what they did here. As you can see here, for example, so there were readings at 1, 2, 3, 4, 5, 6 different points. And most of them come with the same reading. So the green one here is allocated to pyrite. So this dark one at the top there is actually pyrite. And the other one that looks like a light gray is chalcocite. And you can do the same for all of these other grains. Okay. Now you have an idea of what is in each of those grains. And as I said earlier, from just a gray, black and white image, by allocating phases to each of those grains or each of those particles, you have something more informative. So in this case, each of those colors represent different minerals. Okay, and you know exactly what mineral you're also looking at. So the orange one is a particular mineral, we know what it is. The purple one is a particular mineral, we know what it is. And we can look at thousands of such grains or particles and then work out of the thousands we counted, how many of them are liberated or free or made from one single phase, how many of them are made from two phases, how many of them are made from three phases, and so on. So that's basically what liberation means. Okay, so that's one thing we can do. And the other thing we can do is what's associated with. So maybe about 50% of them are made from two phases, and maybe those two phases are maybe chalcopyrite and pyrite. So it tells you that what is associated with what as well, not only whether they're liberated or not, but what's associated with what. Okay. And you can also do ranking. So I'm interested in the chalcopyrite or the chalcocite one. In this case, chalcocite is what's picked in the blue. And basically say which particle contains the highest chalcopyrite and rank them to the particles that contain the lowest chalcopyrite. Okay. So you see that a lot of the particles actually contain the blue phase, which is chalcocite. And you see that if you are trying to recover copper, I think you need to do more grinding, because at this stage, the particles are not liberated. Because I can still see lots of blue phases in each of those particles, and it's telling me that the blue phase is associated with something else. What else? For example, if it's a green, it's boronite. If it's gray, it's chalcopyrite. If it's red, it's pyrite. So again, I know exactly what each color represents in that image. And therefore, I know whether liberation is adequate yet or not, whether I need to do more grinding or not. Okay. And things like this can be decided. And I also know what is the main gangue material I have. Is it quartz? Is it feldspar? What is the main gangue mineral I have? As I said, because if I know the gangue minerals, then we know how we can handle that during processing as well. Okay, more information like mineral abundance, calculating elemental assay, liberation, as I said, can be done on that image. So in this case, for example, just to give you an idea how it's done, that image, for example, is based on part of the work done on about 10,000 particles. Okay, so you can analyze 10,000 particles. Of them, 6,000 something was silicate material. Okay. Or you can say, sorry, grains. Or of them, maybe about 1,600 is made from other oxides that I'm not allocating to because they're not primary phases. Okay, of the 10,000 grains that I have counted, about 700 are carbonates. If I want to know what carbonates, I can also do further analysis and tell exactly what carbonates. Okay. And here it says, for example, 541 grains are copper sulfides. Again, I can go there and work out exactly what copper sulfide. Is it chalcocite? Is it chalcopyrite? Is it a combination? I can work out all those information as well. So by working out lots of particles and lots of grains and determining their exact identity, now we have a complete picture of what's going on. Okay, so abundance of the various minerals that I find in the sample is something we can do from a mineralogical work. Maybe you can stick to grain size analysis and association of minerals with one another and so on. And you can use it for a number of other studies as well. You can do metal deportment. For example, the table here shows two different types of ores of copper. So it was just said copper ore A and copper ore B. So you put it through a mineralogical analysis, and you know, for example, they both come up at about 1.1% copper and 1.5 copper. So they both look okay, reasonable grade. But as I said, just knowing the percentage of copper is not enough. So what else can you do? You can, for example, do what is the proportion of each of these copper minerals in the ore. So chalcocite in ore A is 18%, in ore B is 16%. So I basically take those two ores and I say for covellite and chalcocite. Covellite 10% in one, 1% in the other one. Boronite 7.3 in A, 1.3 in B. Chalcopyrite 53.4% in A and 3.4% in B. And if you look down there, the copper oxides, phosphates, and copper silicates are a lot more abundant in ore B. So already after doing this, I know, oh, so they're both copper ores. They both have more than 1% copper in them, potentially valuable for processing, but they're completely different in terms of mineralogy. So ore A is mainly sulfide copper. Why? Because it says the main phases here are chalcocite, covellite, and chalcopyrite. Ore B is mainly an oxide based. Why? Because as you can see there, the majority, more than almost 70% of the material is mainly made up of an oxide and silicate copper. And if you tell me, am I going to process A and B the same way? The answer is no. Because, for example, for ore A, flotation is a lot more straightforward. Because floating chalcocite and covellite and chalcopyrite, which are sulfides, is easier compared to floating the oxides and phosphates of copper. So already I can tell you, without doing any flotation work, without doing anything in terms of processing, I can say, by just looking at this table, I say, please consider flotation for ore A, maybe do direct leaching for ore B, because flotation is not going to give you benefit that much, unless you do something, okay, to modify the surface of the minerals. So already, I don't need to run a flotation test. I don't need to first have a flotation plant and running and operating to tell you this. I don't need that. I can just look at this table and say, this is what's going to happen. So this table here can dictate what kind of processing plant you're going to have to recover the copper. Okay, so that's how important it is. So usually we don't have the plant and then think about how we're going to process the ore. We first have the ore, do mineralogical work on it, and then decide how we're going to process it later on. Because the mineralogy here is very important in telling you whether you need to do this or you need to do that, or whether you need to do this processing or that processing method. Okay, so that's why it's very critical, and that's why I want to talk about it in today's lecture. Okay, how is it going so far? Is it very familiar? Is it all routine for you guys? I don't know, but let me know if you guys have any questions. Any questions so far? All good? Okay. So far I told you about XRD, which tells you information about mineral phases and so on. And I also talked about SCM coupled with EDS, which tells you about the morphology, the texture of the minerals, and also some information about the grain size, mineral association, and mineral liberation potentials. But what happens if, for example, you have gold? Okay, so you go out there, you found a gold deposit, and usually for gold deposit, you don't get 1 or 2% gold in the ore. That doesn't happen in nature. Maybe you have 2 or 10 parts per million. That's very small. Okay, so in this case, if you do image analysis alone, you may not pick up the gold because gold is very tiny and it's distributed all over the rock. So doing XRD may not tell you that you have gold. So XRD may tell you you have chalcopyrite in the ore, you have pyrite in the ore, or you have quartz in the ore. It doesn't tell you in the pyrite you have gold. Okay, it doesn't tell you that in the pyrite or in the chalcopyrite or in the quartz that you may have some gold. It just tells you that, okay, these are the main phases that you have in the sample. SEM doesn't necessarily tell you that you have gold in the sample because the gold grains may be very tiny in the sample itself. Yes, I said we're looking at maybe 1 micron or 10 micron grains and particles in the scanning electron microscopy. But sometimes the gold occurrence can be that it is very fine in nature. So you could even have elemental gold in the sulfides. So you could have, for example, elemental gold disseminated in the crystal lattice of arsenopyrite. So when you do your SEM, it just comes up as arsenopyrite. And we know in arsenopyrite, for example, we have arsenic, we have sulfur, okay, but we don't have gold. So even though the XRD says you have arsenopyrite, even though the SEM says you have arsenopyrite grains, you may not necessarily know that you have gold there. Why? Because gold can be very tiny, very finely disseminated in the ore body itself, and is not going to be picked up. If that's the case, it's not going to be picked up by XRD or scanning electron microscope. If you are lucky, if you have a very high grade ore, if it's a free gold running all over the deposit, yes, it is possible. You can actually see gold grains or gold nuggets with your eyes. Okay, when you do your mining, it's possible to see gold nuggets. If it's a very high grade ore, no problem. Okay, if it's a free milling gold in quartz, yes, you might be able to visibly see it, or you can probably use just a simple reflected microscope. You can even see it in a simple microscope. But if the gold is finely disseminated in the ore body in submicroscopic scale, then chances are you're not going to tell that from an XRD, you're not going to tell that from an SEM or an image-based method. So because it occurs like that in many places, in fine disseminations, in very low quantities, the option that you have is to do a more detailed quantitative analysis, where the target will be to detect parts per million gold or even parts per billion gold in the ore. Okay, so that's a very low concentration of gold. Would you go and process gold in parts per million concentrations as an economic deposit? Yes, you can. So if I have, say, 2 parts per million gold in the ore, that can be economically extracted. Okay. If you have 10 parts per million gold, that's a huge potential. That's already a very good gold deposit. So to give you an idea, if I had, say, about 1 parts per million gold, you can still extract it economically, but chances are, because it's finely disseminated all over the deposit, you may not necessarily pick it up using your instrumental methods that I just talked about. So what you need to do, you need an equipment that has low detection limit that can pick up even the tiniest amount of gold. And therefore, at least you need to quantify that. Once you quantify, you say, okay, now I have 2 parts per million gold. Then the next step will be, now we know the quantity, the next step will be to find where that gold is located. Then you can use XRD to find the mineral that's hosting the gold. Then you can use SEM-based methods to look for the gold in each of those minerals that are hosting the gold. So I say, for example, now I have 2 parts per million gold in the ore body, but I don't know where it's located. It could be located in quartz, it could be located in pyrite, it could be located in chalcopyrite. Okay, so the quantitative analysis doesn't tell you where it's located, it just tells you there is potentially gold in there. So once you do quantitative analysis, then you say, okay, let's take individual grains of quartz, just like I showed you earlier, and look for the gold by doing spot analysis. Or let's take individual grains of pyrite and see if there's gold in there. So you're now narrowing down. Instead of looking all over the ore body, you're trying to narrow it down to where the gold is located. And typically, the gold is located either in sulfides or in quartz. So that's why I'm mentioning these ones. So if you have, for example, an ore body that says I have gold in, say, chalcopyrite or pyrite, those are usually common associations with gold. Okay, so then we can narrow it down. We can look for where the gold is located, and then we can take it from there. But before you look for where the gold is located, first you have to quantify it. You have to know if it exists. And as I say for this one, you can use equipment or instruments with low detection limits, such as ion beam methods that use ion beams of hydrogen, cesium, and oxygen, and so on. And basically what happens is with this type of equipment, they have very low detection limits. We can take grains of the sample and analyze for the material or the gold or whatever the case may be that you are interested in very low detection limits. And if you were wondering how they work, now in XRD, we say the sample is subject to X-rays. In SEM, the sample is subjected to electron beam. In secondary ion mass spectroscopy, the sample is subjected to ions, so cesium ions and so on. So sample is subjected to cesium ions, a beam of cesium ions, and basically you are fragmenting the sample, okay, breaking the sample literally, and generating molecular products from the sample, okay? And once you break the sample, generate molecular species from the sample, you can use a mass spectrometer to tell you the identity of those fragments. So that's why we say secondary ion is the beam you use, and that's coupled with a mass spectrometer to tell you those fragments belong to gold, the fragments that belong to oxygen, belong to iron, whatever it is. Maybe this picture will tell you what's going on a bit clearly. So here you have a cesium ion or an oxygen ion coming, has a primary beam, hits the sample, literally makes a fragment from the sample, producing lots of secondary ions. If I have gold, what should happen? I should have gold fragments or gold secondary ions fragmented from the sample. If I have sulfur, I should have sulfur ions coming off the sample. If I have iron, there should be iron species coming off the sample. Okay. So then what does the mass spectrometer does? It takes those fragments and based on the masses, okay, of each species, it tells you this particular species that came to the detector had this much atomic unit, therefore must be a sulfur. This fragment has an atomic mass unit of gold, must be a gold species, and so on. So now you know what is in the sample. You also know, based on the abundance of these fragments coming from the sample, if lots of fragments of gold are coming, must be because the sample is high in concentration of gold. Okay. If there are sulfur fragments coming very repeatedly, maybe it's a sulfide sample you're looking at. So you can identify what material you have in there, what composition. You also know how much of that particular composition is coming. Okay, so the point though here is from the mass fragments, we can detect those fragments and measure the mass, which tells us the identity of what is in the sample. But with a SIMS analysis, you can also map those fragments coming from the sample and try to work out and get something like a more visual observation for distribution of each element on the sample. And sometimes if you're interested, you can even go a bit deeper, maybe a few nanometers deeper into the sample and see how the concentration of the particular element, if it's gold, how gold varies as you go deeper and deeper into the sample as well. But this is probably a few nanometers deep. So this may be what you're getting at. So I say, now I did an elemental assay. There might be something relating to gold, or there might be something related to platinum in my sample. I can go detect even the tiniest amount of gold or platinum in the sample. In this case, I say detection limit can be parts per million or parts per million for something like secondary ion mass spectroscopy. Now I know quantity. Now, once I know quantity, then I say, okay, let me then look for those gold or those platinum in the various minerals I have in my sample. Okay, go to pyrite. Let's see if the pyrite has anything. Go to the chalcopyrite. If there's, find if there's gold there. Okay, and platinum or whatever I'm interested in, I can go there and find out exactly where the gold is located. So now you have an idea of how the XRD works, at least in roughly what information I want from XRD. I combine that with image analysis using SEM, where I know about liberation, mineral association, and so on. For something like precious metals, which may be found in very low concentrations in the ore, I can also use equipments that have a lower detection limit to pick up even tiny concentrations of those species. And therefore, at the end of the day, you can have the complete picture of what you have in your sample. Then you can talk about processing, because you did your mineralogical work, you have gained a reasonable understanding of what's going on. Then when someone then tries to come up with a processing plant, it's all to do with using that information of mineralogy into finding the best processing method, okay, for extracting those valuable materials from the ore. Okay, so obviously I was just giving you the highlight or just a rough idea of what each of those equipments can be used for. But as I said, I was also more interested in just understanding and using those equipment for mineralogy anyway. So yes, you may have an understanding of how this equipment is used for other things, but I'm just trying to narrow it down to how they can be used in mineralogy. Okay, so for next week, what I will talk about is more to do with when you say gold ores, what are the common gold ores? Okay, when we say base metal ores, what are the common base metal ores? Or even when you say iron oxide, iron ore, what are the common ones? Because if you don't know that, again, it's not easy to talk about their processing. First, you have to know what you're dealing with, right? Then you can talk about their processing later on. Okay. So I will do that for next week, but I think that is pretty much it for today. Again, maybe I mentioned some things. I remember putting this slide last semester as well. So again, revise these terms, because sometimes I mention them and I just think you guys understand what I mean. But if it's not quite familiar yet, just go through that again and try to be on top of those terms, because they will be very common again this semester. Okay, so that's pretty much it from me, but any questions, any points for discussion, anything you would like to bring up, just feel free to discuss those, or any question on the things I've said so far as well.
Question.
Yes, go ahead, Elias.
In the previous semester, in mineral processing course,
Yep.
We have seen about polished section and thin section in the laboratory using our microscopy.
Is it reflected light microscopy?
Yeah. And
yeah, so most likely, yep.
And as you know,
Sama? Yeah, ይሰማኛል። ቀጥል።
And as you know, when it's about thin section, there is a very type of polished section which is polished in a very thin manner.
Yep.
So when we make analysis using or microscopy, the gang minerals observed as a dark in thin section, while it is lighter in polished section. It's the only difference between thin section and polished section is the thickness of the sample. What makes different their color? The same minerals, for example, if we take one ore mineral and if we are going to analyze using thin section and polished section, the color of the same mineral is different. What makes this different?
I don't know if I understand when you observe two things in a thin section and a polished section. If it's a mineral of the same type, they should appear very similar as far as I'm concerned, unless you're playing with the lighting. So if you look at either a thin section or a polished section or a block sample, usually you can, I don't know if when you say thin section, are they the ones that are embedded in a glass maybe? Is that what you're talking about?
For example, we take pyrite sample, or a gold sample. When we use thin section, just analyze using scanning electron microscope or microscopy. In polished section, the ore minerals is lighter, while in thin section, in polished section, the ore mineral is darker, while as in thin section, it will become darker, lighter. ማለት ተመሳሳይ ሚነራል አሁን አንድ ሚነራል ወስደን ኦር ማይክሮስኮፕ ስንጠቀም ዳር እንትኑ ኦፔኩ በፖሊሽ ሴክሽን ጊዜ ዳርከር ይሆንና ላይተር ይሆንና
አይ ቲንክ ገባኝ የምትለው አሁን
ላይተር ይሆናል
እያልክ ያለኸው ሪፍሌክትድ ላይት እና ሜቢ ኦፕቲካል ማይክሮስኮፕ ነው እያወዳደርክ ያለው። ኦኬ እኔ አንደርስታንድ እንደማደርገው ፖሊሽ ሴክሽን ወይ ቲን ሴክሽን ወይ ደግሞ ብሎክ ሳምፕል መጠቀም ሳይሆን ዲፍረንስ የሚያመጣው ኦፕቲካል ነው እየተጠቀምክ ያለው ወይስ ሪፍሌክትድ ላይት ነው እየተጠቀምክ ያለው የሚለው ዲፍረንስ ያመጣል አፒር የሚያደርጉበት መንገድ። ምክንያቱም ኦፕቲካል የምትጠቀመው ትራንስፓረንት ለሆኑ ነገሮች ነው። ስለዚህ ሞስት ላይክሊ ትራንስፓረንት የሚሆኑት በሚነራሎች ጋንግ ሚነራል ናቸው ሞር ትራንስፓረንት። ኦር ሚነራሎች ላይክ ሰልፋይድስ ዳርክ ይሆናሉ ትራንስፓረንት ስላልሆኑ ማለት ነው ኦፕቲካል ከተጠቀምክ። ሪፍሌክትድ ላይት ከተጠቀምክ ግን ኦር ሚነራሎች ሪፍሌክቲቭ ይሆናሉ ብራይተር ይሆናሉ፣ ጋንግ ሚነራሎች ደግሞ ዳርክ ይሆናሉ። ስለዚህ ፖሊሽድ ስለተጠቀምክ ወይ ደግሞ ብሎክ ስለሆነ ሳይሆን የተጠቀምክበት ላይት ሞድ አንዱ ኦፕቲካል ነው አንዱ ሪፍሌክቲቭ ነው። ሜቢ that's what's making the difference እንጂ የሳምፕል ፕሪፓሬሽኑ አይደለም ነው የምትለው ነገር ከገባኝ።
ገብቶኛል። ስለዚህ ፖሊሽድም ሆነ ሴሌክሽን
ገብቷል። ያ ምክንያቱም እኔ ሁለቱንም አለው በማይክሮስኮፒ
ተመሳሳይ እንትን የሚኖራቸው ማለት ነው።
ሪፍሌክትድ ላይት የምትጠቀመው ብዙ ጊዜ ለሚነራል ሳምፕል በተለይ ሳምፕል ሲሆን
ማለት ነው እንዲያዩ የሚወጣ
ሪፍሌክትድ ላይቱ ከላይ ነው የሚመጣው። ከላይ መጥቶ ሳምፕሉ ላይ ሪፍሌክትድ ሆኖ ከዛ የሚመለሰው ላይት ነው የምታየው አንተ። ስለዚህ ሃይሊ ሪፍሌክቲቭ የሚሆነው ምንድነው ላይት ማሳለፍ ነገር ነው በሪፍሌክትድ ላይት ሞድ ከሆነ ማለት ነው። ስለዚህ ላይት ካላስተላለፈ ለምሳሌ ሰልፋይድ ከሆነ ወይ ጎልድ ከሆነ ላይት ስለማያስተላልፍ ብዙ ላይት ሪፍሌክት ባክ ይሆናል። ስለዚህ ብራይት ይሆናል ያ ጎልድ ሳምፕል ወይም ደግሞ ሰልፋይድ ሳምፕል በምን ሞድ በሪፍሌክትድ ላይት ማይክሮስኮፒ ሞድ ኦፕቲካል ከሆነ ላይት እንዲያልፍ ነው የምታደርገው ኦልሬዲ ሜዠር የምታደርገው ምን ያህል ላይት አልፏል አላለፈም የሚለው ነው ስለዚህ ትራንስፓረንት ከሆነ በደንብ ታየዋለ ጋንግ ሚነራል ከሆነ ታየዋለ በደንብ ጎልድ እና ሰልፋይድ ከሆነ ላይት ስለማያስተላልፍ ዳርክ ይሆንብሃል ስለዚህ አይ ቲንክ two different modes most likely ያ ነው የሚሆነው እንጂ ቲን ሴክሽንም ስትጠቀም ብሎክም ስትጠቀም ፖሊስትም ሲሆን ለእኔ አንድ አይነት ነገር ነው ማየው በሪፍሌክትድ ላይት ሞድ ከሆነ ማለት ነው ስለዚህ ሁሌም ሪፍሌክትድ ላይት ነው ብዙ ጊዜ የምጠቀመው እሱን ነው ስለዚህ ስትጠቀም ጎልድ ሁሌም ብራይት ነው ሰልፋይድስ ብራይተር ናቸው whether I use block sample or thin section it doesn't make a difference I hope it makes sense I don't know ምናልባት ኦኬ ሊሆን ይችላል ግን ማውራት እንችላለን ካልገባን
ግልጽ ነው
ኦኬ ነው ኤልያስ ግልጽ ነው ኦኬ እሺ እዚህ ጋር የምታዩት ይሄ ኢሜጅ
ግልጽ ነው ገብቶኛል
ኦኬ እሺ እዚህ ጋር የምታዩት ኢሜጅ አሁን ሞር ከሪፍሌክትድ ላይት የምታገኙት አይነት ኢሜጅ ነው ኦፍ ኮርስ የኤስኤም ኢሜጅ ነው የሚለው ግን ኤስኤም ኢሜጅ የሚሰራው እና ሪፍሌክትድ ላይት ማይክሮስኮፕ የሚሰራው እዚህ ጋር በጣም ተመሳሳይ ነገር ነው ለዛ ነው አሁን እዚህ ጋር ጎልድ እና ሄቪ ኤሌመንት ያላቸው ሚነራሎች በጣም ብራይት ሆኖ የሚታዩት ለዛ ምክንያት ነው Okay, any other question? Okay, ሌላ question የለም? ኦኬ ጥያቄ ከሌላችሁ ኔክስት መንዴይ ለስራ ስለሚሄድ የሆነ ቦታ ጆይን ማድረግ አልችልም ስለዚህ just check የአሁኑ ሰዓት ይመቻችኋል ወይ ደግሞ ትንሽ ቀድሞ መጀመር ወይስ እንዴት ነው ኔክስት ዊክ በሐሙስ ለታ
ይሁን በአሁኑ ሰዓት ይሁን
በአሁኑ ሰዓት መሆን ይችላል
ይችላል በአሁኑ ሰዓት ስለሆነ በአሁኑ ሰዓት መሆን ይችላል
በቃ ጥሩ እንደዛ ከሆነ ኔክስት ዊክም በዚሁ ሰዓት እንገናኝ ኦኬ ኦልራይት ሌላ ጥያቄ ከሌላችሁ thank you very much I will see you next week
ሶፍት ኮፒዎቹን ላኩልን እንዴት
ኦኬ ያ ይሄንን ልክላለሁ እሺ Right.